Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
And this is Chris Jackson. And we're talking about, I think you had a question regarding accelerated live testing and a question to deal with the slope of some stuff.
Yep, and I did not prepare adequately, but and I did send back a couple of emails. We went back and forth a couple of times on it, but it was an interesting question. It was looking at accelerated life testing where you have multiple stress levels, and when you're doing the analysis, the software packages default that it forces the fit to be a common slope. And the question was, well, why is that? Why does it have to be common? And I thought, well, that's a good question to ask. Because it doesn't have to be. The data is going to be what the data is, and this applies outside of accelerated testing. But I thought this is a good question for Chris because you're the stats nerd kind of guy,
Hey.
Well, you wear the label. It's it fits.
What do you mean it fits? I do plenty of that, but it's not like that. I'd like to think that's the only trick that this pony can do.
No, but I thought, I'm not going to talk to Kirk about it. I threw the statistic at him the other day that, if you took a bunch of stats courses and actually studied it and tried to use it, you have a 38% chance of being good at it. And I'm like, what? Maybe I should have said 36.4% or whatever. What's the exponential? It's somewhere in there.
Oh, you mean there's 67.3 slash 32.7.
Yeah, 32.7. That's the number I was looking for. But anyway,
I think we're losing listeners, Fred.
Yeah, no, we'll get back to it. But the idea was, the question was, I'm noticing this assumption is built into the software, and I don't know what package he was using or was looking at this, and that it's common in articles and so on, is that there's statements, especially like in Wade Nelson's book on accelerated testing, is, well, a check to see if the experiment went well is an indicator that the slopes of the three different stress levels, the time to failure distributions on a probability plotting paper, so they should be straight if they fit that distribution. But furthermore, the slope of each of those should be the same. The same, right. Like in a Y would be the same beta factor, or what's it called? The shape parameter?
Yeah, shape parameter.
Yeah. And so they should be similar. And I said, it's not a requirement. It's something to be aware of, that if it's not parallel, then you need to go do some work to figure out why. It's just forcing it into an assumed straight isn't going to give you a meaningful answer. And so, but the question is, where does that come from? Why do we need to do that?
Well, I think with a lot of reliability engineering statistical stuff, tends to be an element of truth in most of the absurd assumptions and rules that seem to proliferate people who don't want to spend too much time thinking about stuff. Mm-hmm. And I think the kernel of truth, or the element of truth in that, hey, they need to be all straight lines or have the same slopes, is that we know that not as a rule, failure mechanisms, and by failure mechanisms we mean specific ways things fail, for corrosion or fatigue or diffusion or wear. When we plot their times to failure, or the times to failure of those components on a chart, they produce a bell curve or some sort of other curve which always has the same shape or always has a similar shape. So, for example, we know that regardless of how long it takes for a tyre to wear out, the time to failure for a tyre will always have a bell curve shape for the wear out failure mechanism. And different tyres have different thicknesses, and some are used off-road, some are used on-road, so they have different characteristic times they'll fail, but there's a well-known underlying statistical principles behind that mechanism, which means that no matter what, you'll always see a bell curve describe times to failure for that particular failure mechanism.
It just happens somewhere different on the timeline, depending on thickness and road conditions and drive times.
Correct.
Stuff like
which
that.
Which brings it back to accelerated live testing. So if you're accelerating a particular failure mechanism, all you're doing is doing what you're doing, Fred, which is moving where that bell curve sits. Mm-hmm. You're trying to age or wear out that component faster, so you bring that bell curve much closer to the left. So you spend less time testing to induce a failure, but you do it in a controlled way, so you can work out, hey, if this thing failed in 2 days when it was being stressed to at twice a higher level, we can work out through physics that equates to 3 years in real world conditions.
Right.
But the key thing is, it's the bell curve never changes if that's what describes your normal wear out failure mechanism.
Well, the curve not changing is a symptom of that the mechanism doesn't change.
Correct.
Right. And I think that's the step that I think gets missed in software packages and a lot of textbooks, is they say, check this, see the slopes are the same. Well, why? And it's, I use the example of the Arrhenius equation because it's, if you change the temperature, the chemical process goes faster or slower, depending on which way you change it. But it's the exact same process. Right. And if it's not, say you get to a different, you get to a certain point in the heat, it gets so hot that a different mechanism occurs. The amount of energy you're putting into it changes the chemical process. And now the slope will likely be different because it's something else is happening now. So instead of, say, oxygen corroding a piece of metal, if we get to a certain temperature, we melt the metal, for example.
Correct.
And it's completely different now. Or it softens it and it allows the oxygen to work much quicker than it would under normal conditions. And so the change in slope typically indicates that there's some other phenomena either in addition occurring or changing the underlying mechanism you're interested in so that it behaves completely differently. And the danger in that is, and the why we check it and why we want to prove that assumption is true or see it happen in the statistics, is it doesn't make much sense from a physics point of view to melt all the plastic and then translate that down to use conditions where it doesn't even get close to melting and make any meaningful judgment about how long it'll last.
Right. And I think the examples you talked about are quite extreme, where if you're trying to, accelerate plastic embrittlement, but you increase the temperature to the extent it melts, everyone can say, okay, so when I do my accelerated live test, I'll make sure it just doesn't melt, and then I'll be okay. Well, it's a lot more. Yeah,
it's a lot more subtle than that, because the point is why I think plastic is the perfect example. It's not eutectic. It doesn't melt at 118 degrees. It softens. Parts of the polymer chain start to unravel and air quotes here, melt at, say, 80 degrees. And so you could feel like you're way away from where you're in trouble, but unless you really understand that material and how it behaves with difference and stresses, it can change quite dramatically, even at much lower temperatures than its listed melt temperature.
Right. Eutectic's a really cool term there for people who do anything to do with
That's your word of the day.
Is it? All right.
That's the word of the day. Yeah, we got to use that one.
Going straight to Facebook. But eutectics use a lot, and especially alloys and metals and things like that. And if you increase the temperature of a metal, its steady state crystalline structure, essentially the way that atoms want to be arranged, will change. So the actual structure of the metal itself changes. So if you're trying to, accelerate both temperature and fatigue, if you increase the temperature, the way that metal behaves with respect to fatigue cracking is going to be different than that same metal at room temperature. It's not going to be different. It could be different to that same metal at room temperature. So bringing it back, one way to, at least at a high level, can generate some evidence that the underlying mechanism isn't changing, i.e. we're not just simply melting the plastic, is to look at those bell curves, look at the shape of the way our things fail at different stress levels. And if the shape of those bell curves or similar shaped curves doesn't change, it just gets moved to the left as you increase the temperature or the stress or the humidity, it then suggests the underlying failure mechanism hasn't changed. And if the shapes of those distributions, if the bell curve all of a sudden isn't a bell curve when you increase the temperature, chances are you're actually creating a whole new phenomenon that you'll never observe in the real world. And so it's, as opposed to you assuming that they all have the same shape, it's supposed to be checked that they have the same shape.
Right.
Because that then is one of the premises for the assumptions you use to try and convert high stress times of failure to real world stress times of failure.
Well, that extrapolates out. Here's another word of the day, extrapolate, I guess. Maybe we should do that, have a feature of the podcast word of the day, and we could close out with, something like that. We'll have to think about that. But the idea is that there's, two parts to this. One of them is that the assumptions we make are to be checked. And it's one of the things I really liked about Wayne's book is that he would say, now to do this analysis, we're assuming individually distributed or independently distributed and a handful. And then he lists like 3-4 other for that particular analysis, the assumptions we're making. And then he goes into, this is how you see if that's true or if it's true enough that you can move forward with the analysis. And it's one of the issues I have with software is that they almost never flag, you need to check this assumption.
Right.
And so one of the ways, it's a simple check with accelerated testing is you plot it. And if they all look the same slope on a probability plotting paper, you're reasonable there. If in doubt, do the failure analysis, go figure out exactly how it failed. And that can be complex. It could be difficult, but do the due diligence to see it. The assumption also plays a role in how the analysis is done. If they are actually the same slope for the individual stress levels, then it's a easier process to do the regression analysis.
Yeah.
You can solve that problem with reasonable effort. And I remember doing that because I didn't have a computer the first time I tried solving these problems. I'm trying to do, and then I find out that instead of it was a degradation process and they weren't degrading in a constant rate. And so I had some other phenomena occurring. And another piece of this was occurring is that the two high temperatures we were using, both did soften the polymer. And so one of the checks in regression analysis is on the residuals. Are the little perturbations and offsets of what you're fitting the line to, are those offsets constant, or randomly scattered about your fitted line? And mine wasn't. They changed as the temperature changed such that it indicated that the polymers were not the same mass. They weren't. I'm trying to come up with the right word for it. They weren't homogeneous anymore. They were similar to what they were in room temperature. They were subtly different. They were getting softer.
Yep.
And so we were able to understand the chemical process and that softening phenomenon when it started, how it interacted with the underlying. It was still oxidizing, but we were able then to model the effect of the temperature and the effect of that softening piece of it and explain it. But if we hadn't checked the residuals, we wouldn't have seen that.
No.
And so part of all of these assumptions are checks that what you're actually making a conclusion about is probably reasonably supported. We don't just assume it and move on and then trust the assumption's correct. I think that's a trap too many people get in. And so this question was perfect. It was like, no, I need to ask this question and understand it. Why are we assuming that? And that's key. That's what we should do.
And for our listeners who have never heard of the word residuals before, what Fred is talking about is that if you're doing an accelerated live test, which is essentially, for example, you don't have time to confirm if your polymer is going to last 10 years on a solar panel, for example. So if you understand the physics, you can increase the temperature or UV light bombardment, what have you, to essentially equate 10 years in real world to 2 weeks in your highly stressed lab. And the idea is that you'll come up with some sort of indicative life. So 10 years is equivalent to 2 years, but the residuals represent the differences between actual times to failure of your prototypes to the best guess. So if the 2 weeks is equivalent to 10 years in your lab, you'd expect your perhaps your polymers to degrade at 1 week, 6 days, 2 weeks, 1 day, 1 week, and 5.5 days, all clustered around the main value of 2 weeks. And the idea is those residuals, the differences between the middle value and those observed values, tell you a lot about the random nature of failure, which allows you to create a bell curve or whatever it is. And those residuals give you the shape or the nature of, or sort of reflect the shape or nature of the underlying failure mechanism.
Well, I don't think it gives me the shape. I think, so let's say I have 10 data points and I'm measuring whatever, right?
I use the term reflect, not give. So
it reflects it. But the process of time to failure for the individual samples is random. It's going to happen when it's going to happen, and
random but not unpredictable. That's right. There's a method to the madness.
That's right. And so if in any linear, any regression kind of thing is if all your data lines up in a perfect straight line, you're doing an XY plot and you just got a straight line of data. Well, there's probably something wrong with that data. If it comes from a randomly generated process, or a phenomena that has many different factors affecting it. Now, ideally, we want to see the data pretty close to the line that we're trying to fit. And then it's pretty easy to fit a line to that and draw it and say, oh, there's a little bit above and below. Most of the time, the worst case is you get a set of data and it's just a cloud, randomly spaced evenly all about your XY plot, and you can fit any line you want to it because they all equally fit. So one of the ways to determine a good fit is check the residuals. Which one gives me the minimum number of differences from my fitted line to my actual data? Right. And so it's a way to check. And we're getting into the weeds on regression analysis, but the idea is that whether it's assuming that you have a constant or a similar failure rate in your different stress levels, or that your data is from a random sample of a population, or that they're, what does it IID stand for? I keep thinking of that acronym, but it's
independent, individually distributed random variables, or independent, identically distributed random
identically,
variables.
That's the term. Yeah. And if that's not true, then the analysis starts to deteriorate or not be as meaningful. You can still run it. It's one of the wonders of the world is you can always get a number out of a calculator as long as you have power in it.
Yep.
Whether that number is good or not is a completely different process. So the whole sets of assumptions that we make in analysis in lots of our statistics those are the markers of things to be aware of and to check, both in the development and design of the testing that you're doing and in the analysis. And in order to have a supported conclusion from the analysis, well, the assumptions need to be reasonably accurate. And you should check them. In many cases, there's some that are easy to check and others are much more difficult, but it's worth doing.
Absolutely. And you could save yourself and your company millions of dollars if you do that. That's more importantly.
Yeah, exactly.
The worst case scenario is that you actually modify the when you do accelerated live testing, you increase the temperature or humidity or stress levels or whatever it is. Well, there's a couple of worst case scenarios, I suppose, but you might underestimate the reliability. And when you underestimate the reliability, you might be throwing away a perfectly feasible solution to your design problem and go back to the drawing board and try and design something even more robust, perhaps heavier, perhaps more expensive polymers, so on and so forth, when you actually had a perfectly satisfactory solution already. It's just that you underestimate its reliability through mechanisms like the ones we've been talking about.
Mm-hmm. Or vice versa.
Vice versa, yes. You overestimate reliability. So we're ready to launch, ready to deploy, and within a few months, your things start failing in ways that you thought would you'd eliminated through your robust accelerated live testing software package outputs, and
Yep.
you're in trouble. If you're a startup company, you're done. You are bankrupt, and you have to move on to another attempt to crack into the market under a new name.
Yep. Yeah. Now it comes in to be pretty important for businesses. We're going to invest in this accelerated testing, and the very first one I did was on a customer's request. We'll do a big purchase if you can show the data from an accelerated test that it will last our desired time. Otherwise, it's not worth doing. And so my boss never did say no pressure, but every now and then he'd say, "You got any data yet? Is this working?" Because this customer's coming back, on Tuesday, and they want to know, is it going to work? Mm-hmm. And so that was fun, but it was also right from the start. And I was doing a bunch of regression analysis classes in school, and I'm learning about accelerated testing out of Wayne Nelson's book. And he is a statistician, I think, first, and then a reliability person. And so he really did emphasize the assumption. So I learned it right from there. And then there's so many other books and so many other processes. Well, here's the formula, just run it and you're good. And no, there's more to it than that, guys.
Well, I mean, I'm a little bit different, maybe even more. I don't know. You tell me how you think I am in regards to this sort of stuff. Whenever I do some sort of statistical analysis, as opposed to making assumptions, I always try and work out what my best guess of the failure mechanism is. And because you and I both know, we've done a fair bit of statistical analysis. We know, okay, if it's fatigue, it's going to look like this, mm-hmm. rough best guess. If it's those tires we talked about, we got a pretty good idea of what it's going to look like. It's going to be usually a beautiful bell curve, so on and so forth. So as opposed to testing assumptions, I just like, whenever I do anything and I have statistical analysis as part of my job for that day, I want to see where the data points lie out, and do they match my conclusions about the nature of failure based on talking to the people who gave me the brief. Mm-hmm. So if they have, if I'm doing data analysis for a lubrication or for an engine, they say, we're pretty certain that lubrication degradation is causing the issues here. We just want to know how long it takes for the lubrication to last. When do we swap it out? All that sort of good stuff. The first thing I do is do the data analysis and then look at that shape, the shape parameter, the shape of the bell curve or otherwise. And I go, you know what, guys? I don't know if it's lubrication, or more commonly, I don't know if it's just lubrication, because you can see different natures in the same curve. And you do that before you go and do the data analysis, because that data analysis could be based on a faulty premise and no one's happy at the end. So that's how I roll. That might be a similar take. It's essentially restating Wayne Nelson's approach in a slightly different way, but that's how I like doing things.
Well, it's the assumptions aren't to force the data into compliance. The assumptions are things to check.
Yes, true.
I mean, I've seen it where somebody said, well, here's the 3 slopes on their accelerated test. And it says, well, where's the data? He says, well, it didn't fit the line, so I didn't want to show it. Okay.
Excellent. So you just made up 3 lines.
Yeah. Well, no, they forced it to be. The software said, well, they have to be the same, so we're going to assume they're the same. And so the 3 data lines were anything but parallel. They were kind of fanning out across it when they finally got them to put the data on there. And it says, well, just because you assume they're this straight for the analysis, your data doesn't support that. Something else is going on here. Oh,
it's made up.
Yeah.
It's definitely made up.
Yeah. Well, anyway, the whole idea, there's a whole pile of stuff in here. And the assumptions are that you learn something or reinforce something that you already knew about this. And so hopefully we answered the question.
Yeah, it's a good question, though, because, hey, sometimes the best thing you can do is ask questions.
Yep. Yeah, definitely. And so anyway, if you've got a question, that's a good segue. That never happens. If you've got a question about data analysis or anything related to reliability, quality, risk management, safety, all those kinds of things, we'd love to talk to it. We'd love to have you join the conversation. And you can do that over at accendoreliability.com/go/SOR. And you can find a SpeakPipe widget that allows you to record a message to us, assuming you have a microphone. And you can leave a written message if you'd like. You can contact Chris and I and the other hosts of the show over on LinkedIn, or you can find us on our About pages. There's plenty of ways for you to join the conversation, and we would like you to do so. So with that, Chris, I'll assume that you're going to have a great rest of your day. We'll check the residuals later.
I'm going to force my day to align with your assumption, Fred.
There you go. Have a good... Sounds dangerous. Did you not hear anything I said? I'll talk to you later, Chris.
Cheers, Fred. Have a good one.
You too. Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.